Hello. So I just wanted to take a moment and kind of share what I'm going through, what I'm doing. So to start with, this is a brine magnesium hydroxide, uh, not brine, but magnesium hydroxide paste experiment. We will do some brine later, but what I did, I measured out the magnesium hydroxide paste. It's well paste. And as you can see, the scale goes down to milligrams. I put down a bit of aluminum foil at the bottom on these, and I was able, through just being careful with it, adding, subtracting, able to get exactly 10 grams. With, of course, I measured it beforehand, the aluminum foil in the dish, and so that's taken out. Um, and then here's the experimental one. You'll see the little edge. That's a clip attaches to that for the voltage. I didn't think it would work. I thought it would be too fragile, but actually it turned out to be a very cheap and good way to do this. And then I can scrape off and just use a new one later. So here's the setup. You will see I also made sure the gap was 1 centimeter. Of course, this is not like a liquid, so it's not going to be even from the boundary layer, but in Barthacker's results, they found that 1 centimeter gap was optimal for this power supply, 5,250 volts at 0.3 milliamps. So there's a little plexiglass shield so that the ionic wind won't affect it too much. It's a highly localized effect, actually. And we can also, I'll show you here in a minute what it looks like. There's an infrared camera up in the left that you'll see in the back. That's off, but it's actually a Viver, just a little lab mixer, magnetic mixer and some other things. Just a home lab. Okay, you can also see up close, when the lights are out, you'll see a little coronal discharge, but we want to really avoid that if we can. We want to avoid breakdown. Here's the control. I am kind of concerned about it's not even on the surface. Maybe we could smear it somehow. We'll see how this test run goes. This is just the test run. So now the fun part. So here's the infrared imager. On the left, you'll see the max and min, but it takes all this data. You can immediately see on the right, you can even just tell by looking, even though it's jumping around, the min and max of the experimental. You can see it. It's lower. I also really like this software. It's proprietary software from EarCam. You can go and see in 3 dimensions the temperature, and this is very helpful. It's actually a lot more helpful than I thought. You'll see the control on the left, and you can also change it to like lines. But so I'm going to be measuring these, and every hour check the mass, and you can change a lot of this, but really it's not bad for the price and the capabilities. One of the things I like the best, so this is data logging. I set this one because it's a 24-hour test run. It's going to be every 60 seconds, but you can see region 2, that is the control. You'll see the average in the middle, the thicker line, and then the blues are the max and min. You can look out and see it's about 18.5 degrees Celsius. You can see the band there. Then when you look at the experiment, it's very clear that something different is going on. You look at the max, the min, and the average. So average is around 15.8 to 16. So several degrees difference. And then also look at the distribution of it. I mean, the max is like 17.7, changes a little bit, but here we are, just the range is a lot different. And then so if you want to go and look at it, you can. I made sure I avoided the needle, but I do want to get the area directly below it because that's where the effect is happening the most. And it's about a 60-degree half angle out from the needle point. But you can see the foil's reflecting a bit around, but this is a test run. We can also look at a histogram. So I'm also going to get all of this data in this form. I'm working in Python. I need to change some things, but when this is finished, I will be able to take all of this data over 24, 72 hours, whatever it is, and upload it into MATLAB, and you will see. Let's see. Let's try this one. I can show you. Okay, this was for just some saline brine earlier to test. You'll see the red, that's the control, and then the experiment below. I did this for 30 minutes, taking measurements every second or data logging every second. It could be as much as 1/25th of a second. Also some statistics, Welch's t-test 31, confidence interval Welch's test, Cohen's d. Effect size is about 1, anywhere from 0.95 to like 1.07. So pretty good effect size. The p-value, I'll explain that. Well, I guess I could explain it now. So this was a test run. You can see how significant it is. That's like insane. I had to go out 175 decimal places. The reason, I believe, is because when it takes the temperature data, as you can see, 61.99376 degrees Celsius. Wow, it's James Webb 2.2. No. The manufacturer says that the camera has accuracy of plus or minus 2 degrees Celsius. I think this is an artifact. Maybe there's probably some other data in this, or maybe they just hadn't gotten around to to changing it. So it needs to be truncated. I'm writing some Python script actually right now, working through this. But what I need to do is write a Python script that will take these other numbers off, and we just want to look at tenths, 60.8 degrees. And so when we do that, I think that'll bring our p-values down. I mean, I would love to have a p-value that high, but I think it's an artifact of too many numbers here. So, but that's what I'm doing generally. I wanted to record this for my thoughts, but also to share. But this is going to run for 24 hours. Every hour I'll shut it off, and then I need to measure them, and we'll go from there. So I hope you've enjoyed it. I'm improving this as we go along, but I'm monitoring the heat flow using off the shelf, but also the software. Like I said, it's proprietary, but go through there, and we can also monitor the heat flow as well as the mass. So this is actually really good because mass flow and heat flow are parallels, and they're very closely intertwined in this situation. And I think we'll be able to see some patterns and maybe do some analysis using these tools, and they might be useful for other people as well. So we can also go in the emissivity of our materials. This is not water, I'll have to figure out. I don't know what the emissivity is of magnesium hydroxide paste. That is a good question. So we'll have to think about this. But anyway, all right. Thank you so much. I hope you enjoyed this, and let's go on from there.